So we spent a bunch of time talking about the constraints and this magic formula on my right and your right as we look at this. The heat rate is related to mass flow rate and the change in temperature that the heat transfer fluid can get to within the reservoir. So it's kind of an important result for us. We talked about how the temperature change is controlled by our access to the reservoir and the surface area or heat transfer area in the reservoir. We talked about how our mass flow rate was related to permeability and the limited pressure gradients that we could apply. And we talked about chemical impacts and thermal impacts and mechanical impacts on all of those, each of those, I guess, both in terms of maybe shutting off portions of the reservoir by precipitation or opening up by dissolution, and also in the effect on transmission in terms of changing permeability as well. So we talked about the general guiding principles. So now, since we know about those, we need to be able to, I guess, do a couple of things. One is to be able to find resources. We know that for EGS type resources, they're available everywhere, but there must be places that would be better suited to be able to make the reservoir, which we have to create. And for other resources like hydrothermal resources, which we almost certainly know can work well for us because they have probably some permeability, because typically they're in tectonically active areas, we'd like to know how we would prospect for them to find them in the first place. And then secondly, to be able to characterize what is there in terms of other components. And so we'll talk a little bit in the next few sessions about the geological environments for these sites, mainly hydrothermal sites, places where temperatures would be high at low depth within the crust, high elevation within the crust, and where deformation and active tectonics might contribute to make high permeability zones as well. And so finding those places is perhaps the first item. There's something called play fairway analysis. You'll hear a cameo by Jim Folds in one of the later periods that talks exactly about that, what the structural characteristics on the surface that you might recognize that might point to an active hydrothermal system. And so understanding the habits is useful. But then after that is actually being able to characterize it at finer detail, to be able to say what stratigraphic units would be, what flow conduits might be, what the characteristics of the subsurface would be, being able to do that by direct investigation by drilling, and also by using geophysics to be able to cover a much larger volume than we can with drilling. And of course, ultimately, to develop a reservoir, access would be by drilling, which is a big portion of the analysis. And so that's, I guess I've said much of this stuff. The first three I've talked about already. I did pull up this. This is I think this should work here. Bless you. This is the same thing here. I'm curious whether these do work, I think. There is some access which I think are interesting things to go to. So in terms of characterizing these reservoirs, there's access to a 13-year-old October 2013 meeting which had a short course attached to it, which talked about all the kinds of things that we've already been talking about, but perhaps in more detail, and perhaps by some geochemists and people who are actively involved in geothermal prospecting. And so those are marked in this, the notes that we have for this class. In particular, I guess, if I'm looking at this one by Rick Alice, and also this one by Stuart Simmons, I think, as well, looking at very similar things. There's one on here by Jim Folds as well. but there's some discussion on different geochemical signatures to look for in these. And I guess the main component, if we look at it, I think this is the overall view of this, which is a listing of the different segments. So this is here. So if you're interested in this, I don't think you might see some of these later on in the class as we get into this part that's post spring break, and we talk about hydrothermal, EGS, thermal storage, etc., in kind of topical areas. But there are a bunch of these listed here. I didn't mean to do that, but are useful, or at least knowing that they're there if you want to go back to them at one stage. And perhaps some of them might be of use to you in the presentations you are making. So anyway, so that's just a point to have made. So those are there. You can link. I can't link them from my Notability notes, otherwise I'd do that. But you can certainly from the PDF files which you have. And so we'll talk. This is the material that we'll talk about now. So today, perhaps we'll have a bit of a journey around the world looking at these kinds of deposits. But this, as we made the point earlier, is a key relationship for us in terms of mass flow rates and temperatures. We want both high mass flow rates and high temperatures. Perhaps that's less important in EGS, where we think heat is available everywhere, but we want to make a reservoir. Probably not very important at all in ground-sourced heat pumps, because they just work by thermal conduction. And so long as you can actually put the coils in the ground, either by trenching in the surface or by shallow boreholes, that's just fine. But what we'd like to be able to look at maximizing the resource for these deep thermal projects, understanding something about the geology and geophysics, how we might drill for them an instrument to be able to understand what's going on, and then drill wells in it both for testing of flow rates and permeabilities, but also ultimately to be able to recover fluids from the subsurface. And so I will talk about this. This is kind of a plot that explains much about this. So if you're prospecting for a geothermal field, this is a graph that kind of illustrates the relative decrease in risk over time as you put more and progressively more and more money into doing the exploration. So the initial resources, you find a site, there's high uncertainty, high risk if you develop it, but to be able to reduce that risk, what you can do is you can figure out whether it might be a good location geologically, which we'll talk about primarily today. If you think that that's a good bet, you might sink some money into drilling to be able to prove that the reserve exists, maybe $20 million per borehole for deep boreholes. If you think it's a decent project and you've lowered the risk enough to be able to confident that you want to put some more money into it, then you might put some more money into to create production holes and then build the surface plant and then start doing it. So this is quite an obvious way to start thinking about doing this. So the first kinds of things that you do would be to look at trying to figure out maybe what the appropriate locations would be geologically, and then look at whatever information there's available to be able to illuminate your decision. Previous reports of other people that have tried to do some work looking at what the surface expression and photogeology would be to say whether the tectonics is something that would promote it as a decent location. Whether drilling records exist, not very likely for pristine locations on continental locations, but there might be. Certainly if you're revisiting a sedimentary reservoir or petroleum reservoirs that you want to use for geothermal, there'd be a bounty of information available. And then once you think that it's a go, then you might do something before any initial other drilling, but to be able to figure out exactly what's going on. And so that's what we'll talk about. I would say that if you want to figure out some of these things, certainly geochemical signatures, you might look at this Penrose conference from 2013 in Park City to see exactly what there is there to describe that. But the basic idea is that there are certain geological settings which we kind of already know about that would say something about whether a geothermal system is hosted there. And they would be on plate boundaries and in volcanic regions where thermal gradients are decidedly elevated above the background. And of course, they're related. Tectonic areas such as plate boundaries and volcanic areas close to plate boundaries are obviously related and part of the same things. But they could be in terms of these different classifications. I'm not sure this table is very useful. It's better for us to look at it on a schematic. They could be volcanic centers. They could be individual andesitic volcanoes, such as would be existing in the Cascades to the east side of the subduction zone that runs up the western part of the U.S. They could be calderas. Yellowstone, of course, is a caldera. Oregon, Lake Mazuma in Oregon is a caldera also, somewhat dormitory. They could be present in sedimentary basins, and they could be places like basaltic ocean islands like Iceland and the Canary Islands and the Azores, all of which we'll attempt to look at today. So we know the structure of the Earth. We know that the Earth is divided up into a series of tectonic plates floating on the mantle, the upper mantle, which are buoyant, sitting on the mantle. The places where we have destructive boundaries would be the Rim of Fire, where we have plates subducting underneath continents, down through Kamchatka, through Asia, down through New Zealand, along the west coast of the U.S. Much of the U.S. is actually neither a destructive or a constructive boundary, but a neutral boundary, a slip fault, plates sliding each other. And on the western side, we have a slab subducting under the continent of South America, the Caribbean plates with the Windward and Leeward Islands on them, with the plates subducting underneath the Caribbean plate, and areas that we know would be with hotspot volcanoes, Canaries, the Azores, Iceland up here somewhere. And all of those represent different geological habits, if you like. So in terms of andesitic volcanoes, Mount St. Helens, Mount Hood, Mount Baker in the Cascades would comprise that. This would be from west to east for North America. This would be heading out into the Pacific Ocean on this side. So the andesitic volcanoes would be in the calderas. Hotspot volcanism would be in Yellowstone and in the Jimenez caldera, which is where Fenton Hill's lab was close to Los Alamos in New Mexico. Oceanic basaltic provinces would be constructive plate boundaries such as Iceland, where new crust is being formed, and also fault-bounded extensional complexes would be where crust is being pulled apart, and as a result you'd have graben being dropped on boundary faults. These boundary faults are completed by pulling the crust apart, with the possibility that magmatic fluids are high within the crust. This would be like the East African Rift Zone in Kenya, where volcanoes are present, and also similar for sedimentary basins, but also similar to that would be the Taupo geothermal complex in New Zealand. And so these all have specific locations around the globe, and they're all concentrated in places typically close to plate boundaries. So certainly the North Island of New Zealand is one, and we'll go through a bunch of these things just to maybe illustrate what they are. So today will be kind of a world tour. So this is perhaps a more descriptive discussion of what these are. So mid-ocean ridges, Iceland. There's not one off the west coast of the US. Subduction zones, cascade volcanoes would be formed from those. Hotspot volcanism would be where you have rising magma on a hotspot. Cases in point would be Yellowstone and Long Valley. So Yellowstone, big eruptions every 500 million years or so. The idea that you get a fusion of magma onto the surface at that time, and as you evacuate this shallow chamber, then you create a hole, and the surface sediments or volcanics on the surface drop down to be able to fill that hole. And if you're unlucky, maybe it goes up as a major eruption at that time. Places where hotspots exist close to plate boundaries would be regions such as the geysers, where you have a cap rock capping off the reservoir, with regions underneath which are highly permeable, broken by tectonics close to this strike-slip boundary for the San Andreas Fault, and with that region having ample permeability and allowing convection of fluids from depth and gathering them beneath this low permeability cap, which insulates but also primarily stops advection from reaching the surface as individual seeps or hotspots. So I thought we'd go on a world tour today, just for the hell of it. And I guess we had that. Always dangerous to talk about the things that you have, these ones. And so let's start. I'm sad that I'm not going to New Zealand with students this spring break, but that's the deal nonetheless. So we used to run a kind of sustainable energy class by traveling halfway around the globe for a sustainable trip instead of sustainable energy, using about a ton of CO2 per person traveling out there. We'd meet at Auckland Airport on a Monday noon, and we traveled down to Huntly geothermal plant, a thermal plant rather, not geothermal plant. The North Island of New Zealand, close to here, used to have surface mined coal and underground mined coal and coal bed methane, and visit this 1 gigawatt or so power plant. We traveled then up to Taupo. Taupo is on the edge of the Taupo volcanic zone, which we'll have a look at. And so if you look here, I can't draw on this because this is on, don't think I can draw it. No, I can't draw on this. So this is a fault-bounded region, which includes a bunch of volcanoes and very high geothermal gradients that are close to the surface. It's centered on Taupo. It goes out to the coast on each side. I don't know if you can where we can see it. I think this is White Island, or perhaps it isn't. White Island is where they turned the air conditioning on, where maybe a dozen tourists were killed 10 years ago now. They were cruise tourists on the White Island volcano, and it erupted at the time and was a big disaster in New Zealand. But New Zealand is an interesting case in point because they have an abundance of geothermal power, primarily in the Taupo volcanic region. They also have on the river that comes out of Taupo, the river that goes down through Hamilton and to Auckland, is dammed almost at every single location along its length. The replenishment fluids for the geothermal field come from large volumes of rain, which are dumped in the roaring 40s, 40 degrees latitude south. And so there's no shortage of fluids to be able to replenish the reservoirs. And so all the way along the river that goes down to Auckland, there are dams, so it's almost a lake all the way down here. A watershed on the backside of Lake Taupo takes water over the crest and dumps it into this watershed so that all this infrastructure for these dams can be used by the water out of a completely different watershed without damming it, and we'll look at that. We used to visit a wind farm that was right here in Raglan. We used to go to New Plymouth, where natural gas came onshore from the so-called Maui field, which was offshore here, with here. And so if we look at some pictures from that, now you've got a little bit of an orientation for where we are. So a standard, something like a gigawatt geothermal plant, not geothermal plant, originally with 4 boilers and 4 turbines running off those boilers to generate thermal electricity, initially from coal. They have a 5th turbine, which is about 700 megawatts, which generates electricity from natural gas now, which comes onshore from the Maui field that we just mentioned. Control room. So these are the 4 turbines, the generators and the turbines, with steam coming from boilers which are present at the back of this. 4 individual boilers which pass the steam through here. Interestingly enough, for a place that's so has such bountiful water, last time we were there, which is 2023, all of these were turned off because there wasn't enough water to run the turbines to make steam because they were in a drought. So a typical turbine hall with all these things, bunch of students. This is the natural gas turbine that's been added at the end. So a generator with a spindle in it, the turbine at the end, and something like 700 megawatts. A place called Raglan, which is a wind farm with cabooses to stay in, and wind turbines on top of the hill, very large turbines. The Arapuni Dam, which is on the Waikato River. I was trying to think of the name of the Waikato. It runs from Taupo all the way to Auckland and into the sea. Almost every single mile of it is a lake with water impounded behind it, with that water coming from upstream behind that dam and issuing through these the turbine hall into the downstream portion, and then carrying on downstream to get to there with turbines. This is Rodakawa, I think, one of the geothermal plants within the Taupo region. It takes steam that goes into these condensers. These are just turbine blades with cold water passing through it to be able to cool the steam, and so that under this curtain here is just a continuous, basically a rainforest with water dripping down, which is caught and then re-injected into the reservoir. Geothermal pipes transporting the fluids around, steam being issued. Again, a geothermal turbine, no different from the other ones we saw in the steam plant for generating electricity. This generator on the back of a turbine with steam being pumped under high pressure and temperature into it. Control room. And I guess actually the topic of what we'll be talking about Thursday onwards is drilling for access. So this happens to be a geothermal rig. It comes mounted on a truck. So you can see the multiple wheels of the trailer that it lays down flat on. The drill rod for this is in some kind of a cassette, basically, where behind these individual components are maybe 5 pieces of 20-foot so or long drill steel, which gets automatically hoisted into the mast, coupled up with a rotating component here, and then added to the bottom of the drill, which is already in the well. The drill steel is in the well, rotated by this turntable here, which is driven to be able to rotate it, and then pushed down to be able to advance in the well before that's again decoupled, taken up to the top of the mast, and another length of drill steel added to the base. And so you can't really see what's going on here, but it's going into the ground and then drilling beyond. Mixing tanks for mixing cement and for drilling mud to be able to support the pressure which is present here. People standing around. A blowout preventer, so the drill steel goes through this top, goes down into the ground, keeps on going, and this has the ability to be able to shut off the wellhead if something goes wrong, and you're going to get a blowout with very hot water coming out of it, or in oil and gas drilling, oil or natural gas coming out, which of course is an explosion risk, and I don't know whether we have it. This is drill casing that would go down the hell. I don't think in this one we have a tricone bit. That would be the drilling bit. And also in the same location, windmills, wind turbines at different locations. Mount Taranaki, I guess we have these as locations, I think. I guess I don't have a location for that. So if you look at this is on the western, so this is where we talked about before. Hamilton is, or Huntley is where the thermal power plant is. This is Lake Taupo. This is the river that goes down to the coast with all the dams on it. The thermal plants, the geothermal plants that we saw are in here. Wairaki, which we didn't look at yet, would be around about here. And this is offshore gas, comes onshore here. This is Mount Taranaki, and this is that we saw from that physical location. So the Maui gas plant, where it comes onshore from offshore, and Wellington, and a bunch of vines and happy students. So that's kind of the idea of prospecting. So if we look at some of those, and we look at some more. So where we looked at just now primarily was New Zealand. I guess I don't have a picture of the, I guess I do on the right-hand side. So this is the tectonics in New Zealand. The plate boundary comes down here. It switches across the Cook Strait and comes down the center of the South Island. So this is a magnitude 8 capable earthquake fault, the Alpine fault that runs down the spine of New Zealand. Lots more hydroelectric power schemes in the Southern Island just because of the topography. So I guess we know that on the South Island, we know that rho G H Q. So not heat rate, but power from hydroelectric dams is proportional to the volumetric flow rate, the density of the fluid, water, and the elevation drop. And so where you have high elevation and a large volume of fluid, because you have decent sized catchments but also large rainfall, makes it ideal for hydroelectric. And so the big political issue in New Zealand, or one of them, is that the resentment of the South Island, who produce much of the hydroelectric power, to send it over a cable across the Cook Strait to the North Island to be used by the industries there. But anyway, so the plate boundary comes down here and comes down here. The Taupo volcanic zone, as I can draw on here, is centered on Lake Taupo at the bottom. These individual portions at the side are essentially this. The idea that you have a magma reservoir quite shallow in the crust, or with thin crust. As it effuses onto the surface, you generate a gap in here, and as a result of the gap, this block tries to fall down into the gap, and as it falls down into the gap, it maintains these permeable pathways on its flanks, which act as conduits for water present at shallow depths to be able to be returned at high rates to wells in the crust. So that's the basic behavior we have. And so the other different forms of these geological habits would be the geysers, which we already looked quickly at, comprising a cap rock, has enough permeability in the subsurface, high heat flow fluxes because it's close to a plate boundary, ending up with a superheated reservoir which can be tapped at only, these are in feet, not in meters, but only 1,000 meters or so. So very high gradients. Within this, it's permeable, so you have convection occurring. So it's not the normal geothermal gradient that you have with temperatures changing as a function of depth by conduction, but you get this circulation, and so the gradients due to convection are pretty flat. And so the temperatures at depth get transmitted to very shallow elevations within the reservoir. Other forms of these sites would be, well, this is Montserrat, this is in the Caribbean, one of the arc islands within the Caribbean. There's a volcano that's not erupting now, but was erupting since 1996. Now is somewhat dormant. Ended up having the whole southern portion of the island evacuated. The people in Montserrat had the right of abode in the UK, so I think 7,000 people moved to London, leaving 3,000 people on the island living in the north part. And we'll look at some locations for drilling which are in this area here. And so this is the volcano, it's erupting. These are all debris flows or pyroclastic flows or lahars, which are just debris flows, maybe highly mobile flows of ashes and blocks which rush down the volcano, sometimes at hurricane speed, maybe 100 miles an hour if they're gas charged, sometimes remobilized by water. And this actual fan here is a result of this alluvial delta which extends into the Caribbean Sea. So these exist on plate boundaries also. So we looked at the geysers. If I go back here. So again, a different group of students, the geysers, standing around. It's in the coastal range of California. I guess a more accurate location would be this. If I can orient. So as we said, maybe 100 kilometers north of San Francisco. So San Francisco's here, Santa Rosa's the main center. Pliny the Elder from Santa Rosa Breweries, nice IPA. And this is present, this all would be the San Andreas Fault goes offshore in San Francisco. It goes onshore and it runs down through here, through LA. So it runs up through here, goes offshore in San Francisco, cuts off here at Point Reyes, then carries on a strike slip fault up here, and then close to Mendocino, it's still strike slip, but north of here, it's a subduction zone. So the Pacific Plate is subducting underneath the coast of Oregon and Washington and British Columbia. And so all along here, you have Yellowstone must be here, right? Is that right? If I look at this, it makes the type smaller as you expand it. So I can't see if that is Yellowstone or not. And places like Newberry Volcano in Oregon would be in the Cascades. So Cascade Mountains go up this length here. I can't see them so clearly. Baker and Hood, Mount St. Helens would be in Washington State, southern Washington State. And so that's kind of the setting for this. So geothermal pipes taking water and steam from drill holes present on the reservation. I guess these are all trees. I think they were killed by boron coming out of the geothermal reservoir. So it's not emissions free. It's emissions friendly perhaps in terms of low CO2, but not necessarily emissions free for geothermal. Just as we saw at Rotokawa in New Zealand, a condenser, the spent fluids as they've gone through the turbine are exhausted into a condenser. They circulate in a big geological radiator. It's just like not a geological radiator, a mechanical radiator with air being circulated through it to cool it. You can only cool it as much as the ambient air temperature, which in this part of California would be maybe 25 degrees centigrade on average, and then condense the water and send it back to be able to be re-injected. So close to Napa Valley, turbine hall and a condenser unit in the same location, water being brought in from the various geothermal wells which are present on the property, taken through a turbine hall with the spent fluids then condensed and then re-injected into the subsurface. There's a cap rock that's perhaps 1,000 meters thick that enables the material to be insulated at the surface, but most importantly, it stops advection bringing up fluid as seeps. This is one kind of seep that's present there. They're not very abundant, but this may be an abandoned wellbore that hasn't been sealed, or it may actually be a natural seep. I don't know. You see hot water being circulated around the site by these relatively thin, small diameter pipes inside a much larger insulating sheath to be able to keep the heat in as it's taken from the wellbore to the locations where they're utilized. Again, same condenser viewed from a location. Pipes with lots of bends in them, so that when they thermally expand and contract, there's lots of leeway in this elbow junction for it to expand this way and that without straining the pipes. Pipes that go across roadways like this to be able to expand and contract. And this is just, I think these are the off-gassed fluids being sent to the condenser with various plant, which I don't know. Yellowstone, which I couldn't find. Maybe that's Old Faithful, I can't remember. But it's an expression. Obviously, you know that geothermal fluids are present within the crust and at shallow elevation because you see their natural expression on the surface. Yeah.
Are those the plants in California? About how far apart are the injection and production wells?
They are of the order of EGS separations, like 500 meters, half a kilometer. Yeah, I think so. Yeah. But they're much more plentiful. They're much cheaper to drill because they're shallower. So it's 1,000 meters versus 4 kilometers for EGS. And it's much easier drilling because it's not as hard as granites. So I think they're of that order of magnitude. You could look you could Google it and look on a plan view. It would be available. It's of that order. So this is the world's first. Actually, probably I don't think these are. This was taken before smartphones, probably in late 1980s. This is Fenton Hill, or close to where Fenton Hill would be. I've just linked it to Los Alamos because that's where it was based out of. It was in the Jimenez Mountains, and I don't know exactly where on this. The Valles Caldera was where it was located. And so it's in the environs of Los Alamos. So if you don't know where Los Alamos is, it's 80 miles south of Santa Fe in New Mexico, northern New Mexico, in quite picturesque surroundings. Woods, not desert. This would have been in the fall. The aspens are just turning. As I say, this was probably 1990. This project ran 1974 to, it was already done in the mid-80s. This was just the material on site, the cleared off pad with condensers, old condensers. You can see that this is would have a spinning turbine in here, sucking air through a radiator to be able to cool the fluids. It was never used in production like the geysers is. The geysers is about a gigawatt, the same as the big thermal power station we saw in Huntly in New Zealand. So I think it might be the largest capacity geothermal site in the world. Well heads with pipes coming out of it, nothing left. No idea what that tower is. The control room as it would have looked. I don't think any modern day control room looks quite like that now, but abandoned. To be able to monitor flow rates, temperatures, drilling operations. A remnant wellhead still connected up to a pipe, but obviously not flowing any fluid at this particular time, and still not flowing any fluid. So this is the blowout the Christmas tree and the blowout preventer on top of the drill pipe. Again, these are condensers with spinning propellers, spinning fans, I guess, inside the propeller. And so if we're talking about these different geological habits, can't remember where it is. So we made the case that we have locations on fault-bounded extensional complexes. This would be Taupo, New Zealand. The fact that we could have a horse block drop into a reservoir. We looked at land-bound geothermal sites. So this would be Yellowstone, not a geothermal site, but andesitic volcanoes would be Newbury volcano, which was a demonstration site in Oregon, not Q, and Cascade volcanoes. This would be, and also kind of the geysers. It's not andesitic volcanoes. I'm not sure whether it's between these extensional complexes. This is be close to the geysers in California, and basaltic. Actually, the other andesitic volcanoes would also be Montserrat. Its own country in the Caribbean. And so that would be this particular location here. And I mentioned that because the photos were coming up were exactly that. So this is the exclusion zone. The whole southern 2/3 of the island were an exclusion zone with limited access. I haven't been there for a while. This is the actual erupting volcano with spines coming out of it from outside the exclusion zone. The newly built volcano observatory, which wasn't yet operational. And here are the former town of Plymouth, Montserrat. So maybe a town, maybe a town with a population of 3,000 with now a population of 0. A clock tower which would have been 20 or 30 feet tall at one time, that now hasn't been covered by lava but has been covered by reworked, rainfall reworked alluvial deposits carried down from the volcano and then deposited on a different side of the fan that I pointed out before on the western side of the island, but the same process, just transported from high up. Yeah, the former town of Plymouth, a thriving metropolis, but no longer. So these would have been taken in the early 2000s, I guess. GPS being used to monitor what's going on. Drilling actually close to the site that I pointed out using a particular kind of exploration rig rather than production rig to drill down to, in this particular case, 200 meters to put in seismometers and tilt meters that are deep enough that the noise from the surface doesn't register because you're 200 meters deep, and the signal to noise ratio is much higher. drilling 24 hours a day because the rig's on site, so you might as well use it all the time. Unrelated, but the nearby island of Martinique, where Mount Pelée erupted in 1908 and killed 20,000 people with a pyroclastic flow that rushed down the mountain, and the only person to survive in the particular environs of the town of Saint-Pierre, I think, was a guy called Osiris, who had been put in jail for being drunk. And because he was in this structure, he survived, and everyone else did not. Is that the last one? And so, also related to these other locations. So the other thing with these sites, you don't really see much on the surface, and you certainly don't see anything here. So this would be on a plate boundary. In this particular case, this would be pointing northwards in this direction here. So this is on the edge of a plate boundary. Whoops. And the plate boundary runs not through here, but in this direction. And so the North American plate is subsiding underneath here. And it does it further to this direction, which I guess is the east. This is north. And so Martinique is further down this chain of islands in the Caribbean. And I guess I was pulling up other locations where hotspots exist, are such as in the Rhine-Graben. So I don't have a location map on this. We'll look at it soon. So this is the Rhine River. It runs north-south on the French-German border into the Page, and then turns left and goes to the Netherlands, which is basically the Rhine Delta, the low-lying lands of the Netherlands. And because it's being pulled apart and these horse blocks are dropping down on these faults, then you get hot fluids rising and a high temperature gradient at this particular location. So Sulz is the existing EU geothermal project, which has been running since the 1990s. Has a bunch of deep wells that go down to 5,000 meters, of multiple splits from them for both injection and recovery. So this isn't a conventional hydrothermal reservoir, but it's an EGS reservoir. I guess it is producing a small amount of power. I guess they probably put it in the grid because you have to use the power if you generate it. And it exists on one of these interior boundaries to a continent. And if you look at a heat flow map or a temperature map at particular depths, you find this anomaly in terms of flow. So if you could measure the temperature on the surface in some way, satellite imagery, or by measuring the temperatures in wells, you can make such heat flow maps to be able to allow you to zone in on certain areas. And so this isn't very exciting. This is the site. This is the sign for the site. I didn't go on the site at a particular time, just driving past it. But this is the Sulz project in the Rhine-Graben. West coast of America, I think this is Mount Shasta, which is part of Shasta, Hood, St. Helens, Baker, Rainier, as you go up the Cascades in this particular case. This is Mount St. Helens. Mid-1990s, it erupted May the 18th, 1980, killed 60 people, but shut down aviation and life in the western U.S. for a few months. There was a big bowl-shaped collapse and a lateral blast. So the side of the volcano slumped, released the pressure to a shallow magma chamber. The magma went from solid with lots of gas in it to gas blast and blew everything down the mountain and blew over hundreds of square miles of forests as a result of the lateral blast. I think this is one of the dams which was put in after the fact to catch all of the sediment which was being eroded off the surface. Again, this amphitheater. And this was 2 years after the eruption. the kind of moonscape downstream, where all this work, all this material, just like in Plymouth, had been reworked by rainfall and rivers in carrying it downstream. So similar to Sulz, which is a graben in a continent, this happens to be Wairaki, which is near Taupo, which is graben in a volcanic region. So the same deal. You have these side faults and blocks which drop down as the magma evacuates at the sides and leaves a void, allowing the rock block to drop down into it. Same kind of behavior. We're looking at this from an overview. These are the pipes supplying hot water to a centralized geothermal plant somewhere down here, going across roads, lifting it above the roads, but also allowing expansion. These pipes would be seated on rollers, so as they expand and contract, they're not physically anchored, but they just sit on a roller which is able to allow them to move laterally. Greg Bignell from GNS. And I think this must be Rotokawa, the first site we looked at for the big green condenser. And I guess what's notable here is that the geothermal plant, which produces electricity by flashing the water, is also used in a secondary use to be able to dry lumber. So this is a lumber mill, and it's used to be able to dry the lumber that comes from the local region. I guess this is a water steam separator. Water comes in at the bottom. It's turned around. The water flashes to steam. The steam vaporizes and is taken off the top, and the water is removed. So perhaps this is the inlet, perhaps this is the outlet for water, and perhaps this is the outlet for steam, which makes sense. I think this is acidification to be able to make sure you keep the reservoir and the turbines from not dropping silica and plugging up. I think we looked at this already. It's the same site. This is rainfall underneath here. So all underneath here is water dripping down from having condensed and being caught and then re-injected. And then this is White Island. This is the one that, don't know if I can see it. It's offshore Rotorua. Rotorua is a big geothermal hot spring spa. And I don't know. I think actually this might be, it's either this or this. And this is the volcano that erupted with a bunch of tourists on it. Actually, does it say? Might be a Maori name. I think it was further offshore than that. Yeah, Wairaki. This is White Island. So the Maori name is Wairaki Wakari, I guess. And the European name, I guess, is White Island. So this is what erupted 10 years ago? I can't remember. A bunch of people didn't survive, and a bunch of people came back on shore with terrible, terrible, terrible burns. Where the gas comes on shore at New Plymouth, this is the name of which escapes me, Taranaki, Mount Taranaki, a perfect Fuji-style volcano, a stratocone, still active, but not heavily active. And hotspot volcanoes, this I think is Taburiente in the Canary Islands, which is just off the west coast of Africa. Don't know if I have it on here. Yeah. So on the island of La Palma, so just for a location. So this is off the west coast of Africa, Spanish territory. The other hotspot volcanoes would be, I think, the Cape Verdes, the Green Islands, the Green Cape. What's Cape mean in Spanish? Cape of Good Hope is it land for? Cape of Good Hope is at the south of Africa, and these would be the Azores up here, and this would be Iceland, obviously up here. So Mid-Atlantic Ridge runs down here. These are not on the Atlantic Ridge, but there's a cross portion of that ridge here. Cape Verde's here, and if we go back to look at these, so this is Taburente above the clouds, and this, as a curiosity, is the Azores. Again, volcanoes in the middle of the Atlantic, a stopping point for Christopher Columbus, maybe, I'm not sure. Certainly a stopping point as you go on the southerly route west from Spain into the Caribbean or southern North America. And so this is the Azores. And all this is cooking food. So these are a bunch of pits which are dug close to on a geothermal field, maybe 4 feet deep, big enough in diameter to be able to take 18-inch maybe diameter pot, lowered in here, and then backfilled with volcanic ash on top, left for 2 hours, and then returned to be able to eat your food. And finally, I think these are the last ones. This is Svartskeni, I think, in Iceland. So I don't think that's the actual location. Mid-Atlantic Ridge coming up into Iceland and across the Reykjanes Peninsula. Many of the geothermal plants here. Krafla, I think, is up here also. And so the main accessible geothermal plants are close to Reykjavik. Useful not only because, well, there's hot water everywhere in Iceland, but there's not very many population centers. I would imagine that 80% of the population of Iceland live in Reykjavik, and so it's supplied by hot water for district heating, but also for conversion to electricity. I think this is Svartskeni, which is close to the Blue Lagoon. We looked at this in a prior class. This is on Svartskeni. This is a Carbfix project where they're re-injecting water with carbon dioxide dissolved in water with the idea that you can permanently fix the carbonate underground, where even if the reservoir gets breached because it's mineralized, the CO2 isn't released. You can only do it where you have a ready source of heat at high elevation, shallow elevation, because it doesn't cost too much to drill, and the heat catalyzes this retrograde reaction. And the interesting thing is that in depositing carbonate in the aquifer is that it still keeps on accepting more fluid rather than completely destroying its permeability by the deposition. The Blue Lagoon, or the effluent fluid from Svartskeni site, which is close by, which they very cleverly use to entice you to spend $40 a person to go and sit in it in a place that's close by. This is the actual effluent pool, not the Blue Lagoon. And you can buy cocktails to sit in the hot tubs and have a nice day. I think this is Thingvellir geothermal plant, which is also on the Reykjanes Peninsula. It's very close to the Mid-Atlantic Ridge. I think we saw Roger Ballard diving on the Mid-Atlantic Ridge in one of our earlier classes on the plate boundary, touching both plates at the same time. This was the home to Iceland's parliament, right on this spreading ridge, and this is the Thingvellir plant. We looked at this before. This is Geyser in Iceland. The moniker for geysers around the world. Iceland also. And this is a strange name place. You went there. Can you pronounce this place? You went there with your green. Hellsdottir, or don't remember. I think this is actually tagged because it was an actual location. So I can't pronounce the name of this. But this is another geothermal plant. They have guides. These are 4 different wellheads issuing into 4 different locations. The physical plant with generators and turbines driving those generators, all very clean. And I guess that's it. Where are we for time, by the way? 1:08. Was it? Did I have another one? Was I going to show? Yeah, this is true. Reykjavik in Iceland. Also, this is curious because the other use for large volumes of hot water is to dispense with snowplows. And so this is underwater heating, bathroom underfloor heating for streets in Reykjavik. So instead of plowing, if you have so much abundant hot water, you can circulate it in the subbase below roads and directly melt the material. Quite clever, quite useful. I think this is Svartskeni as well. Obviously, if you're prospecting for this, you don't have to be too clever because you can recognize that you have high heat flow and abundant fluid flow at shallow depths. Perfect location for a geothermal plant, very pretty. Again, a very clean plant, pulling water into a turbine hole. The pipes being relatively small diameter, maybe 6 inches inside sheathing, which is perhaps 18 inches in diameter to keep temperatures. Very picturesque. You know what those are, condensers. And plant taking geothermal water in, flashing it to steam, inlets and outlet as a larger steam volumetric flow rate. Svartskeni, Blue Lagoon, somewhere here, the plant, turbine holes, supplies from a wellhead along insulated pipes, again, mainly insulation, relatively small diameter pipes inside that. I think Iceland's parliament, Reykjavik's cathedral, Nesvellir, we've already seen it, a dam. Yeah, this is the ancient Icelandic parliament. These blocks are the rocks that are being forced apart by magma coming up between them and pulling apart, leaving a amphitheater in which the ancient Icelandic parliament was held, and somewhere else. That's in the UK, not related to geothermal. So I don't know how much we talked about these individual components. We've seen all of these, and that's really all I wanted to do. The one we perhaps didn't introduce, so we talked about Taupo being a extensional basin in volcanics with high heat, such as this. We talked about this for Sulz, which is a sedimentary basin, which is being pulled apart. The one we didn't talk about the structure so much for was these hotspots. And so the hotspots we looked at were the Canary Islands, Cape Verde south of them. We looked at the Azores, cooking our seafood. We looked at Iceland, and some random other places around the world. Again, concentrated on constructive plate boundaries where we're making crust rather than destroying it in subduction zones in the system. And the mechanism of these hotspot volcanoes is that a plume of hot magma is present below shallow crust, and as a result of this, it diffuses onto the surface. But because these are on parts of the crust which are moving above these hotspots, you tend to get, you can't see it, I guess the famous one, of course, would be Hawaii. And you probably know that the Hawaiian Islands, which I don't have photos of, would be a chain of islands with the big island and many more smaller islands emanating from it. And the reason for that is that you have a static hotspot which doesn't move, a plume coming out of the mantle, and above it the plate is translating, as in plate tectonics, towards a subduction zone. In this case, it would be net moving, I guess, to the east, because all the smaller volcanoes are dotted downwind of it. And the reason for that is that the plate is moving in this direction. Does that dispel that? Well, if the plume is static and the plate is net moving, has to be moving in this direction, right? To be able to make this so that the older volcanoes would be ahead of it. The volcanoes have been made 2 million years ago, would be further to the west of this, and therefore the big island would be left with the largest one of these. So the mechanism by which that occurs. So, all by way of, I guess this is it, yeah. Hotspot stays static, the plate moves, so you have this trail of volcanoes which are come from it. And then, yeah, this would be the plate motion that comes from that. So, the big picture behavior that we'll talk about, have talked about, is being able to understand exactly where these locations would be. And so the next information we might want to do would be doing either drilling on this site to be able to prospect to see exactly what the scale of the resource might be. But before doing that, we might do something even less expensive, which would be doing some kind of geophysics to be able to prospect for what's pleasant. So the next thing we'll talk about, and we'll start talking about that next time, will be what kind of geophysics we can do on the surface or in boreholes, but typically on the surface, to be able to spend not very much money to be able to get a big picture of the subsurface structure, to be able to provide clues as to whether it may be a viable geothermal reservoir or not. So we'll talk about that on Thursday. So that's it.